Hi folks, let's look at another problem relating to uniaxial stress. So in this example, it reads as follows. A brass tube of 50 mm outside diameter, bore 40 mm, and of length 30 mm is compressed between two end washers by a load of 25 kilonewtons, and the reduction in length measured is 0.2 mm. Assuming Hooke's law applies, thus, if we assume that the material is deforming within its elastic limit, we've been tasked to calculate the elastic modulus, or the Young's modulus, and the expected answer is 53 GPa. So how do we go about calculating this problem? So in summary, this is a quick schematic of the problem, showing the brass hollow tube being compressed between two washers, as shown in the diagram. We've got the 25 kilonewton force compressing the tube, and I've also indicated the diameters of the tube. So the external diameter is 0.05 meters or 50 millimeters. The internal bore, or the inner diameter, is 0.04 meters, and the length is 300 millimeters or 0.3 meters.
Right, let's work through this problem. So we have our brass tube. Is being compressed by a 25 kilonewton force. The length of the tube is 300 millimeters, and from the problem that we have, it's actually a hollow tube, so the internal diameter is 40 and the external diameter is 50. So let's note this information down. So dn is equal to 40 millimeters, so that's the same as 0.04 meters. Diameter out is equal to 50, so that's the same as 0.05 meters. As I've previously stated, it's more or less up to you whether you want to work in the base of millimeters or in meters. You just have to be very careful when it comes to converting from meters to millimeters in terms of units for stress, for area, for volume and things like that. So as long as you are aware of how you need to convert it, it's more or less up to you. The deforming force, or the compressive force, is 25 kilonewtons, which is the same as 25,000 newtons. So what else do we need to know? We need to know something about the material, and that information hasn't been provided, so that's what we need to work out. So what is the Young's modulus for the given material? Now we know that the material is brass, so I think what we can do afterwards is to look at the material database and see if the value that we get is equivalent or falls within that range for brass. Okay, so what else do we need to know? We've been given some information regarding the reduction in length. So the change in length, delta L, is equal to 0.2 millimeters, or 0.2 times 10 to the power minus 3 meters. Now here it's more or less up to you. Because we're dealing with a compressive force and we have a reduction in length, we can denote these by negative, but the negatives will cancel out. So it's more or less up to you how you want to more or less go about defining this. So the first thing that we need to do is to calculate the strain. So we're going to do this in two ways. We can either use the linear deflection formula. So linear deflection, or the change in length, is equal to f times the length, original length. Now let's denote that original length, divided by the area E. So let's call that equation 1. Or we can work out the stress, work out the strain, and use this relationship to figure out what E is by dividing the stress by the strain. Okay, so let's call this R2. So we've got two choices in terms of how we need to go about calculating for the Young's modulus. Let's use the deflection formula. So change in length delta L is equal to the deforming force times the original length, all divided by the cross-sectional area times E. So if we transpose this equation and make E, which is the Young's modulus, the subject, then E will be equal to F times L naught over A times delta L. And if you look at this expression very carefully, if we were to group these variables, you realize that F over A is the same as the stress, and the original length over the change in length is the inverse of the strain, because we know that strain is equal to what? The change in length divided by the original length. So either techniques will give you the same result. Okay, it's just that this is a shorter alternative. So E is equal to, so let's put in our values. So we've got 25 times 10 to the power of 3 times the original length, which is 0.3, over, we know what the change in length is. That's been given as 0.2 times 10 to the power minus 3. But we haven't worked out the area. So how do we work out the area? So let's work out the area first, then we come back to this equation. So the area is equal to the area of the outer diameter minus the area of the inner diameter. So we have to assume that the tube, okay, is a solid of 50 millimeters, which has been hollowed out. Okay, so we're taking out and it's due the length of what? 40 millimeters. Thus this equation. So using the engineer's formula, we've got pi over 4 d out squared times minus pi over 4 times d in squared. So we can factorize the common term. So what is the common term? Pi over 4. So pi over 4 into bracket the diameter out squared minus the diameter in squared. And here we go. So all that we have to do now is to substitute known variables. So what do we know? Pi over 4 into bracket 0.05 squared minus 0.04 squared. So what would this give us? So let's bring our handy calculator. So let's work out what's in the brackets first. So we've got 0.05 squared minus 0.04 squared. Okay, so that gives us pi over 4 times 9 times 10 to the power minus 4. Okay, so that is meter squared. And when we do the needed computation, so we multiply that by pi over 4. And that gives 7.0686 times 10 to the power minus 4 meter squared. So we worked out the area. So we can now go back to our established equation. Okay. Right. So now that we've worked out the area, we can now substitute the value for area into this formula. So we've got 25 times 10 to the 3 times 0.3 all over 7.0686 times 10 to the power minus 4 times into bracket 0.2 times 10 to the power minus 3. And there we have it. So we can now do the needed computation. So the Young's modulus is equal to, so let's do the needed computation by multiplying 25,000 by 0.3, and that gives 7,500, all divided by 7.0686 times 10 to the power minus 4 times 0.2 times 10 to the power minus 3, and that gives 1.41372. Let's just write the whole thing, times 10 to the power minus 7. Okay, so if we do the inverse of that times 7,500, that gives 53.052 times 10 to the power of 9 Newton meter per meter squared, which is the same as 53.052 G N per meter squared, which is the same as 53.052 G P A. And there we have it. So let's use alternative 2. First principles. So we've calculated the area, so we don't need to calculate that again. So area is equal to 7.0686 times 10 to the power minus 4 meters squared. We know F to be 25,000 newtons. So therefore, the stress, sigma, okay, is equal to force divided by the area, which is equal to 25,000 divided by 7.0686 times 10 to the power minus 4. So that we have to do is do the needed computation. So 25,000 divided by 7.0686 to the power minus 4. And that gives, lost it. Let's do this again. 25,000 divided by 7.0606 minus 4. And that gives 35.37 MPa. So we've worked out the stress. So the next part is to work out the strain. So strain epsilon is equal to delta L over L naught. So this would be equal to 0.2 times 10 to the power minus 3 divided by 0.3. So we do the computation. 0.2 times 10 to the power minus 3 divided by 0.3. And that gives 6.6667 times 10 to the power minus 4. So we now have values for strain, value for stress. So therefore, the Young's modulus, which is characterized by A, is equal to the stress divided by the strain, which is equal to 35.37. So just to let you guys know, because we've rounded up some of the numbers, we're going to have a slight variation to what we got previously. So we need to bear that in mind. But it will more or less be the same value, hopefully. 0.6667 times 10 to the power minus 4. So all that we have to do is put in our values, okay, divided by 6.6667, 10 to the power minus 4, and there we go. And that gives 53.055, okay, times 10 to the power of 9 PA, okay, which is more or less the same as 53.05, let's call it 06 GPA. And there we have it. So either alternative should give you more or less the same result.
So this is a quick summary of what we just worked out. So we start off by calculating the area of the brass tube. So the cross-sectional area A is equal to the difference between the area of the outer diameter and the area of the inner diameter. So this gives pi over 4 into bracket the outer diameter squared minus the inner diameter squared. So putting on values into this equation, we get pi over 4 into bracket 0.05 squared minus 0.04 squared. So this gives pi over 4 times 9 times 10 to the power minus 4. And when we do the needed computation, we get a result of 7.0686 times 10 to the power minus 4 meter squared. We then proceed to calculate the stress in the tube. So stress in the tube, sigma, is equal to F over A. As we've already pointed out, F is equal to the compressive force and A is equal to the cross-sectional area of the hollow brass tube. So this equals to 25 times 10 to the power minus 10 to the power 3, divided by the worked out area, 7.0686 times 10 to the power minus 4, which gives a result of minus 35.37 megapascal. So as I stated in our work along, it's up to you if you want to use the negative signage. But from the problem, the negative signs will cancel out, so it's more or less up to you. We then proceed to calculate the strain. So based on the information that we've been given the measure of the reduction in length. So the reduction in length equated to 0.2 millimeters. And we've been given the length of the tube, so the original length is 300. So if we use the formula, strain, which is characterized by epsilon, and that's equal to delta L divided by L, that will be equal to minus 0.2 divided by 300. If you want to, you can convert the lengths into meters, and you still get the same result. So the result that we get in terms of the strain is minus 6.66667 times 10 to the power minus 4. Thus, we've got the needed information to calculate for the Young's modulus. Thus, the Young's modulus, E, is equal to sigma divided by epsilon, or the stress divided by the strain. So this equates to minus 35.37 times 10 to the power of 6, so don't forget mega is a million, divided by minus 6.6667 times 10 to the power minus 4. Once we do the needed computation, we get approximately 53.06 GPa, or 53.1 GPa. Alternatively, we can use the axial deflection formula. So again, we don't need to calculate the area because we worked out the area to be 7.0686 times 10 to the power minus 4 meters squared. So using the axial deflection formula, the reduction in length, delta L, is equal to F times L divided by A times E. F characterizing the external force that's causing the structure to deform, L representing the original length, A the cross-sectional area, and E characterizing the elastic modulus of the Young's modulus. So if we're making the Young's modulus the subject of this equation, then the Young's modulus will be equal to F times L divided by A times delta L. So we then proceed to just put in known variable. So as we already know, F, the compressive force, is equal to minus 25,000. The original length is equal to 300 millimeters, but we're converting everything into meters, so that will be 0.3, divided by 0.2 times 10 to the power minus 3 times 7.0686 times 10 to the power minus 4. We do the needed computation, and that gives approximately 53.05 GPa, which is the same as 53.1 GPa. And there we have it. All right, folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session as we look at further examples relating to uniaxial strength. So please share and subscribe, and I'll catch you in the next section. Bye for now.